In this video, we are going to look at potential difference and Ohm's law. Potential difference and Ohm's law. We're also going to look at IV characteristics of conductors. We're also going to look at resistance and resistivity as well as power. Right, so potential difference and Ohm's law. Now looking at this circuit here, we have a power source, that is power supply, and then we do have arrows showing us the direction of movement of electrons in the circuit, right? And then we've got a bulb which is on, right? So electrons are moving from the negative terminal of the battery to the positive terminal, while conventional direction of current, we know it is from positive to negative that way. So in an electric circuit, the current transfers energy from the battery to other parts of the circuit, e.g. a lamp. The PD across the lamp is the energy changed into heat and light energy per coulomb of charge passing through it, or the work done per unit charge in moving the charge between 2 points in the circuit. So there we are, the PdV is equal to energy transferred over charge. So V is equal to W over Q. 1 volt is the potential difference between 2 points in a circuit when 1 joule of electrical energy is transferred for each coulomb of charge. So remember, I said in the first video, you need to establish the formula first, and then you put quantities of 1 on each. So 1 volt will be equal to the energy transferred, as says the PD between 2 points when 1 joule of energy is transferred per unit charge, or when 1 charge flows through the circuit. At the battery, each coulomb of charge takes a fixed amount of energy and delivers it to the lamp. In the lamp, the energy changed into heat and light energy as electrons collide with the filament ions and transfer energy to them. The coulombs return to the battery to be supplied with more energy. So what are we saying? We've got the charges moving, right? So as the charges move in the circuit, they tend to lose their energy. Remember, energy cannot be created nor destroyed, but it is converted to other forms. So the energy is being converted to light and heat in the bulb. Now if you connect a resistor like this, energy is dissipated as heat in the resistor. So when they get back to the power supply, yes, they tend to get rejuvenated and given more energy and dissipate that energy until we deplete the energy that is in this battery or the source. Now we always connect an ammeter to measure the current, and it is connected in series in a circuit, and we measure the voltmeter across a component. We measure we connect the variable resistor to control the amount of current that flows in the circuit. So if you make a coil of constant and wire using between 1 and 2 meters of wire, that's 0.4 millimeters of diameter, then separate the turns so that they don't touch. Switch off the supply or disconnect the coil when not making a measurement to prevent the coil heating. Check the 0 volt reading. Don't just assume to be 0 amps. So this is a practical that you're doing. If you repeat the reading does not agree with the first reading, then it may be that you're leaving the charge flowing too long and heating up. So if you then plot a graph of PD against V, PD or I against PD, I against PD, you get a straight line that passes through the origin, assuming that the temperature must be kept constant, like we're saying. We get values, so we'll be adjusting the current here, okay, adjusting the current there, or adjusting, yes, and then reading the PD and the current, so adjusting the resistance there, reading the PD and the current. So you should get a straight line graph that passes through the origin, even getting to the negative quadrant. So here you have to reverse the terminals of the battery, and you get this graph as well. So this graph tells you that the current is directly proportional to the PD. Remember, there are two conditions for direct proportionality. That is, a straight line graph is obtained, and then secondly, it passes through the origin. This is known as Ohm's law, which applies to metal or metal alloy wires as long as their temperature remains constant. So what does Ohm's law state? Ohm's law states that the current through a metal wire is directly proportional to the PD across it, provided that the temperature and other physical constants remain constant. The resistance is constant and does not depend on the current or PD, but depends only on the physical conditions like temperature or mechanical strain. Now, IV graphs. The IV graph of a metallic conductor, we have shown that it is a straight line that passes through the origin. The IV graph of a filament lamp is like that, so it curves outwards like this. Okay, so if you had to reverse the terminals like we did on the metallic conductor, it then goes the other way, it then curves the other way. The IV characteristics of a thermistor curves inwards like this, and then that of a semiconductor diode, it curves pretty much the same as that, but then it gives a sharp rise at a certain value of voltage, and yes, sharp rise, and then does not conduct in the negative bias. Okay. A filament lamp gives the curve with a decreasing gradient because its resistance increases as it becomes hotter. Resistance increases with temperature because the positive ions on the conductor vibrate more at higher temperatures, and the charge carriers cannot pass through as easily when a PD applied or is applied across it. Metals have a positive temperature coefficient because their resistance increases with an increase of temperature. A thermistor at constant temperature gives a straight line. The higher the temperature, the greater the gradient. The same result is obtained for a light-dependent resistor in respect of light intensity. So we only consider negative temperature coefficient thermistors as well as negative coefficient LDRs. Heating an intrinsic semiconductor, e.g. silicon, frees additional electrons and holes. So the resistance decreases with increasing temperature, giving a negative temperature coefficient. A silicon diode conducts easily in its forward direction above a PD of about 0.6 volts and hardly at all below 0.6 volts or in the opposite direction. Now, resistance and resistivity. Resistance is the ratio of the PD applied across a conductor to the current passing through it. It's given by the formula R is equal to PD over current, V over I. So V over I. So I will be equal to V over R. And also if V is equal to IR. So 1 ohm is 1 volt per ampere. The resistance of a component in circuit is a measure of the difficulty of making current pass through the component and is caused by the repeated collisions between the charge carriers in the material with each other and with the fixed positive ions of the material. So we can say that it is the friction or the opposition to flow of current offered by the atoms that make up that conductor. Resistivity. What factors affect the resistance of a wire? The length of the wire, right? The longer the length, the more the resistance. The shorter the length, the less the resistance. Cross-sectional area. A bigger cross-sectional area means less resistance. A smaller cross-sectional area means more resistance. The material. Nichrome wire has more resistance than copper wire. So now we are talking of resistivity of the material. So we're talking of the resistivity. The greater the resistivity of a material, the better, the higher the resistance as well. So what do we say? Resistivity is a property of a material. So nichrome has its own resistivity, therefore it has got its own resistance per unit change in the temperature or time. Then we've got copper wire as well, it has got its own resistivity. So resistivity is a property of a material. Temperature. In metals, a hot wire has more resistance than a cold wire. Now if you plot a graph of R against L, it's a straight line passing through the origin. Plot a graph of R against 1 over A, it's also a straight line passing through the origin. Remember from graphs, if you plot a graph of R against A, it's supposed to be an inverse relationship. That's the graph of Y against 1 over X. Right. The constant of proportionality is rho, which is resistivity. That is, remember we said that R is proportional to L, R is inversely proportional to A. So the constant of that proportionality is called resistivity. Every material has got its own resistivity. Good conductors have low resistivities, e.g. copper has a resistivity of 1.7 times 10 to the power of minus 8 ohmmeters. Resistivity is defined as numerically equal to the resistance of a sample of material of unit length and cross-sectional area, and the unit is ohmmeters. Right, so lastly we want to talk about power. From the definition of PD and current, we have PD, remember it's equal to the work done per unit charge. Work done per unit charge when charge is transferred from one place to another in a circuit. Energy transferred in the lamp will be equal to VQ or QV. Now we know that Q is IT, so it's going to be VIT. For example, the PD across the lamp is 12 volts. This means that 12 joules of energy transferred per coulomb, right? So 12 joules are being transferred per coulomb in the circuit. Right, so 2 amps means that 2 coulombs per second. So 2 amps here, remember, current is equal to charge over time. So it's going to be 2 coulombs per second passing through there. The lamp is kept on for 100 seconds, and the energy transferred is equal to VIT, which is going to be equal to 12 times 2 times 100, 2400 joules. Okay, now since we know that V is equal to IR, we can substitute for V here to get IR times IT, which then boils down to I squared RT. So also we know that V is equal to IR, right? So making R the subject there, making I the subject gives you V over R. So if you put V over R right here where there's I, it gives you V squared over RT. Okay, so this T is not supposed to be on the denominator. It's supposed to be on right there on the numerator. So it's V squared over R times T, like that. I think I'm okay right there. Yes. So this is V. Yes, V squared over R times this T, correct. Now, power is the rate at which energy is transferred. The power of the lamp is equal to 2400 over the time, so energy over time. So from that the example that we have up there, so 2400 over T, which is 100 seconds, giving you 24 watts. So dividing by T, it then yields VI. We have removed the T. Remember, energy is VIT, so power is energy over time, so we have removed the T from there. So power alone becomes VI or IV. Since V is equal to IR, we can now say power also is equal to I squared R. We are substituting for IR right there. So it's going to IR times I, giving you I squared R. Then here substituting for I, V over R becomes V squared over R right there. So these are the formulae that we apply when finding the power. So this is the end of the video. Please let me know in the comments where you need further clarification. Signing out.